Hello everyone, our new topic is called Systems of Linear Equations. In this topic, I am gonna give you detailed information about systems of linear equations. When we are talking about a system of linear equation, we are considering more than one equation at the same time. In this topic, our main goal is to find a solution of the system of linear equations. And the solution of the system of linear equations will be the solution of each equation at the same time. Okay. Introduction to linear systems. First, I'll give you basic examples of linear systems. Two lines in the plane and two planes in the space. Two lines in the plane. From the geometry, you know that two lines in the plane is in three situations. They are parallel, they intersect and coincide. To define the situations of lines, first we will define the equation of the line and we will look for the solutions of each equation at the same time. If the equations have a common solution, then lines will intersect. If there is no common solution, then the lines will be parallel. If there are infinitely many common solutions, then the lines will coincide. Okay. A line in the plane OXY is represented by this equation. Here x and y are variables, a, b, c are real parameters, and a and b are not zero at the same time. This equation is called a linear equation. Suppose that we have two lines L1 and L2. L1 is given by this equation, L2 is given by this one. Then, as I said before, the intersection point of L1 and L2 will be the solution of this system. And here, as you know, this line has three situations. The system has a unique solution, then these lines intersect, and vice versa. The system has no solution, then these lines are parallel and vice versa. The system has infinitely many solutions. In this case, these lines are coincide or the same, and vice versa. That's it. In this lecture, in order to solve a system of two linear equations of two variables, we will use three methods: substitution method, Cramer method, and matrix inversion method. Resolution using substitution method. The method of substitution allows to solve linear systems by substituting one variable with the expression of another one. Example. Let's solve this linear system. In order to solve this system, first we express y with x or x with y. Let's express y with x in the first equation. From here, then y will be 1 over 2 minus 3 over 2x. And we use this substitution in second equation. It will be 2x minus 7 times 1 over 2 minus 3 over 2x is equal to minus 2. From here, y is 1 over 2 minus 3 over 2x and x is 3 over 25. If we write the value of x in the first equation, the value of y will be 8 over 25, x is 3 over 25, that's it. Then the solution of this linear system will be an ordered pair 3 over 25, 8 over 25. That's all. Resolution using Cramer method. Suppose that we have this linear system. If the determinant a1, b1, a2, b2 is different from 0, then this system has a unique solution x, y. And x is defined by this expression, y is defined by this one. When we calculate the value of x, in order to get the determinant in the numerator, we replace a1, a2 with c1, c2 in this determinant. When we calculate the value of y, in order to get this determinant, we replace b1, b2 with c1, c2 in this determinant. Example, solve this linear system. Here t is a real number. Here we use Cramer method. First we calculate the determinant of t minus 2, 3t. It will be t squared plus 6, which is different from 0. Because of this system has a unique solution. X will be the determinant of 1 minus 2, 1t, divided by the determinant of t minus 2, 3t, is equal to t plus 2 over t squared plus 6. Y will be the determinant of t1, 3, 1 divided by t minus 2, 3t is t minus 3 over t squared plus 6. Because of this, the solution of the linear system will be t plus 2 over t squared plus 6, t minus 3 over t squared plus 6. That's all. Resolution by matrix inversion. Suppose that we have this linear system. Using the parameters of equations, we define these matrices. A is A1, B1, A2, B2. X is XY. B is C1, C2. If we calculate the multiplication of A and X, it will be A1X plus B1Y, A2X plus B2Y, which is column vector C1, C2. As you see, we write C1 instead of this expression and C2 instead of this one. Because of this, A times X will be B. And vice versa. If we assume that this is true, in this case, this matrix will be this one. From here, A1X plus B1Y will be C1. A2X plus B2Y will be C2, this one. Therefore, this system and this matrix equation are equivalent. This means that finding the solution of the linear system is to find the matrix of X. Okay, let's look at here. The system S is equivalent to the following matrix. AX is equal to B, where A is the matrix of A1, B1, A2, B2, X is the matrix of xy, B is the matrix of C1, C2. The matrix A is called the coefficient matrix of the system S. If the determinant of A is different from 0, then the matrix of A is invertible and the system S has a unique solution. Here, in order to find the solution of system, we solve the matrix equation A times X is B. This equation is equivalent to this one. The inverse of A times X is equal to the inverse of A times B. The inverse of A times A is identity matrix, and identity matrix times X is X. Because of this equation will be equivalent to this one. X is the inverse of A times B, where X is the matrix of xy. As you know, X will be the solution of this matrix equation, and X and Y will be the solution of the system S. In order to calculate the inverse of A, we use this expression. That's it. Example. Solve the linear system S. Here T is a real number. We take the matrix of A is 1, 1, 1 T square, and the matrix of B 1 T. Here the determinant of A is equal to T square minus 1. As you see here, we have two cases. The determinant of A is 0 or is not 0. Suppose the determinant of A is different from 0. First case, T square minus 1 is different from 0, is equivalent to T square is different from 1 is equivalent to T is different from plus minus 1. In this case, then A is invertible. And the inverse of A is equal to 1 over T square minus 1 times the matrix of T square minus 1 minus 1, 1. The matrix of X will be the inverse of A times B is equal to 1 over T square minus 1 times the matrix of T square minus 1 minus 1, 1 multiplied by the matrix of 1T is equal to 1 over T square minus 1 times the matrix of T square minus T minus 1 plus T is the matrix of T over T plus 1, 1 over T plus 1. Then the solution of the system will be T over T plus 1, 1 over T plus 1. If you want, you can take the solution as a set of this element. Second case. T is 1. In this case, the system of S will be this. X plus Y is 1, X plus Y is 1. Two equations are identical. Because of this, the system has infinitely many solutions. The solution of this system will be the pairs of X, y such that y is equal to 1 minus x and x is any real number. Or this one, the pairs of x, 1 minus x, where x is any real number. That's it. Let's look at the third case. T is minus 1. In this case, the system will be this one. X plus y is 1. X plus y is minus 1. From here, x plus y will be different from x plus y. It's impossible. Because of this, the system has no solution. The solution set is empty. That's it. I explained substitution, Cramer, and matrix inversion methods for two equations of two variables. But these methods work for any systems of linear equations. Let's look at second basic example of a system of linear equation. Two planes in the space. A plane in the space OXYZ is represented by the linear equation AX plus BY plus CZ is equal to D. Here, X, Y, Z are variables, A, B, C, D are real parameters, and A, B, C are not zero at the same time. Let's consider two planes, P1 and P2. Here P1 is given by this equation, P2 is given by this one. From the geometry, we know that two planes have three situations. These are either parallel or the same or intersect along a straight line. In order to define the intersection of these planes, we solve the system of these linear equations. So, the intersection of P1 and P2 is the solution of this system. Then we can say that if two planes are intersect, then S has an infinitely many solutions. If these two planes are parallel, then the system has no solution, and vice versa. If these planes are the same, then the system has an infinitely many solutions. Exercise. Find the intersection of P1 and P2. As you know, in order to find the intersection of P1 and P2, we must solve the system of equations 7x plus 2y plus 2z is 1, 2x plus 3y plus 2z is 1. From here, if we look at the first equation, 2z will be 1 minus 7x minus 2y. If we write this expression instead of 2z in the second equation, it will be 2x plus 3y plus 1 minus 7x minus 2y is 1. From here, z will be 1 over 2 minus 7 over 2x minus y. Second equation will be minus 5x plus y is 0. You see here we cancel 1 and 1. Then y will be 5x, z will be 1 over 2 minus 7 over 2x minus 5x is equivalent to this one. Z is equal to 1 over 2 minus 17 over 2x, y is equal to 5x. This is the parametric equation of the intersection line. Okay, that's it. We can stop here. If you want to write the solution of this system, the solution will be the set of x, 5x, 1 over 2 minus 17 over 2x. Here x is any real number. That's all. See you guys next lesson.